In this video, we're going to review the cross product. The cross product, or vector product, multiplies perpendicular components of two vectors to give a new vector that is perpendicular to both of the original vectors. So if I draw two vectors, a and b, the cross product, which is written with an x or a cross, hence the cross product, similar to the way a dot product is written with a dot. Now there are two directions that are perpendicular to a, in this case a vector pointing up or a vector pointing down. To find the correct direction, we use a right-hand rule because our coordinate systems, by convention, are right-handed. We first point our fingers along the first vector, in this case a, curl our fingers toward the second vector, or in this case b, and our thumb will point in the direction of the new vector, which in this case is up. Now notice that the order matters. If we swap a and b, our thumb points down in the opposite direction. Mathematically, this means that when we swap the order of the two vectors in a cross product, we pick up a minus sign, or it points in the opposite direction. So it's very important to pay attention to the order since the cross product is not commutative. Now the result of a cross product is a new vector, which means we have to worry about the magnitude and direction. This was not the case with a dot product because the result was just a scalar or number. In simple cases, like when the two original vectors were crossing or in the xy plane, for example, then we know the new vector is either pointing parallel to the positive z-axis or negative z-axis, and we find which one with the right-hand rule. To get the magnitude of the cross product in this case, we can simply take the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. Again, just as with the dot product, this angle should be when the vectors are drawn from the same point. I'll now go ahead and write some of the properties of the cross product. First, as we've already said, the cross product is non-commutative. It's actually anti-commutative, which mathematically means a cross b is equal to minus b cross a. It is also distributive. So if we have a cross the sum of two vectors b and c, this is equal to a cross b plus a cross c. And finally, using the definition of the cross product, since no vector can be perpendicular to itself, the cross product between any vector and itself is 0. So if you cross any two vectors and get 0, you know they are parallel to each other, because otherwise some amount of the vectors would be perpendicular. Now since our Cartesian unit vectors are all perpendicular to each other, we get to write the relationships between them using a cross product. If we move in a cyclical order from I to j to k and back to I, crossing two unit vectors will give us the next unit vector in the cycle. So I hat cross j hat gives us k hat, and so on. If we swap them or have them go in the other order, we simply pick up a minus sign. And as stated before, any unit vector crossed with itself is 0. Now with that, we can evaluate the cross product in general for any two vectors in 3D space. There are two ways to evaluate the cross product. The first is just by distributing, which is what I use most of the time. To do this, we write both vectors in Cartesian form and distribute them term by term. Now, if you actually know your vector components, then you can do this with numbers and it works the same way. We can ignore any like terms because we know they go to 0. Then we just need to be careful to find the direction of each term and place our minus signs. When we group our terms, we get this. Now you don't need to memorize this. When you're actually evaluating a cross product, you will multiply your numbers, group the like terms by direction, and you're done. But back to this result. The I, j, and k terms correspond to the x, y, and z components of the new vector. Notice a few things. First, the x component only depends on y and z. The y component only depends on x and z component only depends on x and y. Second, each term has a minus sign in the middle, and before the minus sign, the components are in order, x, y, z, and the second term after the minus sign, they are in reverse order. And once you see this, it starts making memorizing or checking your answer very easily because you pick up on the pattern if you do enough cross products. The second way to evaluate a cross product is using a 3x3 determinant. In our matrix, the first row contains our unit vectors, the second row contains the components of the first vector, and the last row contains the components of the second vector. To evaluate a 3x3 determinant, we first break it into three 2x2 determinants. If you're not familiar, the determinant of a 2 by 2 matrix with components A, B, C, D in this order is equal to AD minus BC. We often imagine going from the upper left to the lower right, multiplying, and then subtract the upper right times the lower left. So you kind of do this little swirl. Now to break our 3 by 3 determinant into 3 of these 2 by 2s, we first take a unit vector, so we pick one, starting with I hat usually, and multiply it by the 2 by 2 determinant that does not share a row or column with that unit vector. So I hat will multiply the 2 by 2 determinant containing y and z components. Then we add the next 2 by 2 determinant. For j hat, I like to wrap back around to stay in order, stay in cyclical order, but you don't have to. You simply need to remember to add a minus sign in front of the j hat component. Now we just evaluate each of the 2 by 2 determinants and get the same result as before. When you do this method, you do not need to rewrite each 2 by 2 determinant once you're comfortable, like I have done. You can simply fill out the 3 by 3 matrix and go through each term, which many people seem to like. Both of these methods give the components as the result of our cross product. If we want the magnitude of the vector that we get from our cross product, we can simply take these x, y, and z components and then combine them using the Pythagorean theorem to get the magnitude. So that's it for the review of the cross product, and I'll see you in the next video.